So last but definitely not least, Leah Bar. It's a work with Ben-Shaul, Dalia Fishelov, and Sochen, Tel Aviv University.
Okay, hi, thank you so much, Tami. Thank you for the brave people that stays. This is a joint work with Ben-Shaul and Sochen from the math department in Tel Aviv University and Dalia Fishelov from the math department in Afeka College. So the basic topic of this talk is about eigenvalue problem. So find the eigenfunction and eigenvalue of operator is very fundamental task in physics, chemistry, and engineering. For example, Schrödinger equation, molecular physics, vibration analysis, geology, bridge construction, mechanical engineering, shape analysis, and much more. This is a very, very important problem. So let's set up the problem. We have some differential operator L. L is a differential operator. Okay, it's not a matrix. It's a self-adjoint operator. For example, the Hamiltonian of the Schrödinger equation. Lambda is the eigenvalue, and u of x is the eigenfunction. And our goal is to find the eigenpairs, lambda I and ui. So basically, this is kind of solving a PDE problem. Because L is, again, is a differential operator. So usually we use standard method like finite element and finite differences. But these methods have some limitation. For example, this solution may suffer from high condition number. They're highly dependent on the discretization. It means how we discretize the finite element or the mesh in the finite difference. If we have high order derivatives, they are very, very sensitive to noise. And interpolation and extrapolation are not straightforward in these methods. So we suggest an alternative approach, which is based on machine learning on neural network. So how can we solve this problem by neural network? So let's start with the architecture. It is very, very simple. It is based on fully connected layer, fully connected network with smooth activation function. It is very important that it is smooth. For example, ReLU is not appropriate for this purpose. So the input to the network is the coordinate x1, x2, and so forth. And the output is the solution U. This is the eigenfunction. This is the output of the network. And the question is how we train this network in an unsupervised fashion, such that it solves the eigenfunction problem. So this is an explicit representation of the neural network. And if we take a smooth activation function, for example, siren, G-law, hyperbolic tangent, and so on, we can see by the construction of this network that U is infinitely continuous. This is very, very important. Okay, so this is the architecture. How do we train the network? So what we are doing basically, we take our domain and throw points inside the domain. So the blue points are the points inside the region, and the red points represent the boundary of our domain. And what we are going to do, in every mini batch, we build a loss function such that the equation that we want to solve is satisfied for every point. So that's why it is not, there is no supervision, it is unsupervised. Okay, so we take care of the point to satisfy the equation that we want. I will explain it in 1 minute. So the advantage of this approach are threefold. The algorithm is mesh-free, so we don't need to discretize, we don't need meshes. The points can be arbitrarily sampled, and we don't have any limitation on the number of points that we throw inside the domain. Secondly, the domain is not limited to standard shapes like circle, rectangle, ellipse, and so on. It can be arbitrary. And this is a very, very important advantage. And lastly, the derivatives are analytically calculated. Why they're analytically? That is because of the structure of the network, because it is infinitely continuous, and then we can calculate the derivatives of this network, and we can do it by automatic differentiation. So if we are using torch, we can use the autograd function. If we're using TensorFlow, it's a tf.gradient. So we have built-in functionality to the gradients to have an explicit derivatives of any order that we want. Okay, so let's start with a very, very simple example that we want to find only one eigenfunction when the eigenvalue is known in advance. So Tu is defined as Lu plus lambda u, and we want it to be equals to 0, okay, because this is the eigenvalue problem. So lambda is known in this case. So what is the loss function that we train our network? So I will explain the loss function now. The first term is the L2 fidelity of Tu. What does it mean? It means that if Tu, which is Lu plus lambda u, goes to 0, it means that u that satisfies this condition actually solve the eigenvalue problem. This is what we want. So we want to minimize the Tu in the L2 norm. The second term of the loss function is the L infinity fidelity term. It means that we want to minimize the largest deviation, the largest errors of this Tu. So we want the L2 norm minimize the error in the average sense, and the L infinity decreases the largest deviations. Okay, this is another contribution of the loss function. The third one is the boundary condition that we want to be satisfied. Then we have some normalization because we want the eigenfunction to have some magnitude, and we add some weight decay. So this is the loss function that we train the network. It runs very fast for 1D and 2D, like a few minutes. And here we can see the results. So we have a very simple neural network. The input is X, the output is U of X. We have only 5 layers. Each layer has 26 neurons. And here we can see an example. If we have in one dimension the second derivative of u plus 4u, this is the boundary condition. The ground truth is the sinus 2x. This is what we expect to obtain. And after we train the network, you can see after 100 iteration, 500 and 1,000, we can see that the model bring us very close to the ground truth. Okay, now what happens when we don't know the lambda in advance? So this is the more interesting case when we have only the operator and we don't know the lambda. So what we are going to do, we want to find the smallest eigenvalue. Okay, this is the setup. And the question is how to do it. So for that, we use what is called Rayleigh quotient. This is the quotient between the inner product between Lu and u divided by the magnitude of u. And the property of the Rayleigh quotient is that if u is an eigenfunction, R of u is the eigenvalue. This is the corresponding eigenvalue. So now our loss function is Lu plus Ru. So R represents the eigenvalue. Okay, so we have the same loss as before, but we add another term which minimizes the Rayleigh quotient. This means that we promote the solution towards the smallest eigenvalue. Okay, so here is the result. We have the second derivative of u plus ru. This is the ground truth is sinus kx, and the smallest k is 1. So here we can see after 1, 50, and 1,000 iterations, we can see that we obtained the ground truth result. Okay, the next one is a more challenging task when we want multiple eigenpairs, that we want the m smallest eigenvalues. So for this, the output of the network is the set of the eigenfunction that we want. So again, we have the basic loss function that we had before, but we have the sum over m, over all the eigenfunction that we want. We have the L2 norm of the Rayleigh quotient. I will not get into all the details here. And the last thing that we impose orthogonality. Because we know that the eigenfunction are orthogonal, we can impose it in the loss function. And here we can see the results. The eigenpairs are k squared and the sinus kx. And here we can see the result. This is 100 iterations, 500, and 1,000. And we can see that we found both the eigenfunction and the eigenvalues. Next, we solved also for the 2D Laplacian operator. The ground truth is the multiplication of sinus nx and sinus kx2. So the architecture, we build one network for each eigenfunction. And here we can see the results. After 1,000 iteration, here we can see the 4 eigenfunction with the 4 frequencies. This is what we expect. Here we can see the quantitative results in terms of PSNR and RMSE. We get very good results, and also the error in terms of the eigenvalues. Again, we compared ourselves to Krylov base and to spin, to other methods, and we show good results in terms of PSNR and RMSE. The last 2 examples are consider the free-form domain. So in this example, the domain is not a rectangular. We took a rectangular and we took a hole in it. So we have an arbitrary shape. And our algorithm doesn't care about the shape because we just throw the point inside. So here we can see the ground truth on the left. We can see the model output. So outside this white circle, okay, what we see inside the circle is just extrapolation. It's not interesting, but we see that we got a very good error. And the last example is the L-shaped domain. So we see, we compared ourselves to the finite element method, and we see that you get very, very close results to the finite element method, which in this case we afford as the ground truth. So in this case, we proved that the method works. In the paper, we added also theoretical aspect, where we relate the truncation error. It means the error of the L2, which acts on U, with the approximation error of the function itself. I mean, what's the relation between them? So we have some theorem that make the relation. In addition, we related the total number of weights to the truncation error, and you can see in the graph that with the large epsilon, when we have large error, so the number of weights are less. So this makes sense, but we have all the equation that support it, and this is experimental results. Okay, so to conclude, we suggested a neural network-based framework for the eigenvalue problem. The algorithm is mesh-free with the free-form domain. We solve several eigenpairs simultaneously. We showcase several use cases in different dimensions and difficulties. Now we are working on also on 3D, but basically it can be extended to any dimension. We show convergence bounds relating approximation error to truncation error. And in future work, we are going to address higher dimension, non-uniform sampling, and more complicated equations. Thank you very much.
Thank you, Leah. We have some time for questions. Maybe I will ask one. So I was wondering if there is any effect on the sampling distribution of your training points on the output, the accuracy of the
very
output.
Good question. I mean, right now we sampled uniformly, but this is another direction for research because we think that maybe more clever sampling can increase the results. I mean, maybe sample more near edges or near more to have some more criteria how to sample. But this is another direction we are thinking about.
Thank you.
Can you a little bit expand about the image motivation, like
the motivation for this?
Yes, I know that your motivation was from images, but can you a little bit expand?
I mean, it is a very general problem, but for example, for shape analysis. I mean, in shape analysis, when we take the eigenfunction of the Laplace-Beltrami operator, the lambda can help with the matching shapes. This is an example, but it has many, many applications.
Thank you.
So let me see if I understand, it's a convex optimization, right?
Convex?
So it's convex problem. So no? So
no,
how can you be sure that you get to the right solution, or how can you make it to converge to a right solution, the correct solution, because there are more than one solution?
Well,
if it's not convex, I think it has more than one solution, right?
It's not guaranteed. It's not guaranteed, but practically, if we have enough points, if you have enough sampling points, practically it converges to the right solution. Practically, but it depends. It depends on the parameters of the network, about the tuning, the learning rate, all the hyperparameters. It depends on them. But the main thing is the density of the sampling points. If we have enough points, very dense, so usually we get good solution.
Yeah, I actually asked this because you have this loss term that it combines many terms. It's L infinity and L2 loss and the boundary condition. So how can you know, maybe weighting them or something could help be sure that the boundary condition is better preserved than the L2 and the L infinity or something like that? Did you try this combination?
We have the hyperparameters. I mean, we have some. We didn't. I mean, we played with this. It was quite stable. All the hyperparameters are listed in the paper. It was quite stable for few applications. And to debug this problem, we look at the loss function. I mean, how it behaves. It behaves normally, and we fine-tune the hyperparameters. But basically, if we have enough sampling points, it works quite well.
Thank you.
Thank you, Leah. Let's thank the speakers, all speakers. Thank you, the organizers, and you.